Hello friends. In this video, we're going to understand what a tree is in computer science, and why this structure quietly appears almost everywhere in modern software. At first glance, a tree just looks like connected circles and lines, but underneath it's really a way for computers to organize information hierarchically instead of sequentially. An array stores things in a straight line, one item after another. Trees work differently. One piece of data can branch into multiple smaller pieces, almost like folders inside folders on your computer. The top element is called the root. Every connected element below it is called a child node, and nodes with no children are called leaf nodes. Now here's the interesting part. Trees exist because many real-world problems are naturally hierarchical. File systems, website menus, organization charts, HTML documents, game scenes, even AI decision systems all behave more like branching structures than flat lists. And once you notice that pattern, you start seeing trees everywhere in computing. In the next slide, let's look at why computers actually prefer trees for many operations. This is where trees become extremely useful. Imagine searching for a name inside a giant unsorted list. The computer may need to check elements one by one until it finds the correct value. That becomes expensive as the dataset grows. A tree reduces that work by splitting decisions into branches. A binary search tree, for example, keeps smaller values on one side and larger values on the other. So instead of scanning everything, the computer keeps cutting the search space in half. That tiny structural difference changes performance dramatically. And underneath, modern CPUs love predictable decision patterns like this, because fewer memory locations need to be touched. Less memory movement usually means faster execution. This is also why databases, file indexes, and search engines heavily rely on tree-like structures internally. Even your operating system uses trees to organize directories and scheduling information. The important idea is not the drawing itself. The important idea is that trees reduce unnecessary work by organizing relationships intelligently. Next, let's look at one of the most common tree structures developers use everywhere. A binary tree is one of the simplest and most important types of trees in computer science. The word binary simply means each node can have at most two children, a left child and a right child. That small limitation turns out to be incredibly powerful, because it creates very efficient navigation patterns. Computers can move through the structure almost like playing a guessing game. Smaller or larger, left or right, again and again until the target is found. Now here's the subtle part people often miss. Trees are not physically stored in memory like neat diagrams. Underneath, memory still looks like raw addresses and bytes. Each node usually stores data plus references, pointing to other nodes somewhere else in memory. So the tree shape is really created through links between memory locations. And this is exactly why pointer mistakes can completely break a tree structure in low-level languages like C or C++. Binary trees become the foundation for many advanced systems, like heaps, syntax parsers, database indexes, and AI search algorithms. In the next slide, let's connect trees to things you already use every day. One reason trees matter so much is that they model how many real systems naturally behave. Take your file system. A folder contains more folders and files. Those folders contain even more things underneath. That's a tree. Web browsers work similarly. When a web page loads, the browser converts HTML into something called the DOM tree. Every button, paragraph, image, and menu becomes part of a hierarchical structure the browser can navigate efficiently. Game engines also use trees. Objects inside a game world are grouped together so movement, lighting, and rendering can be processed in layers instead of recalculating the entire world every frame. Even machine learning decision systems often branch like trees internally. And here's the deeper engineering reason this keeps happening. Trees help computers localize complexity. Instead of treating everything as one giant flat system, they divide work into smaller connected regions. That makes searching faster, updates cleaner, and large systems easier to manage. Now let's finish by building the mental model you should remember from this entire topic. So here's the mental model to keep. A tree is really just a way for computers to organize relationships efficiently. Instead of placing everything in one long sequence, trees create structure. That structure allows software to search faster, update data more cleanly, and manage complexity without scanning entire systems repeatedly. And underneath all the abstractions, the machine is still doing something very physical, following references through memory from one node to another. That's why tree design affects real performance. Memory movement, cache behavior, traversal cost, and update complexity all depend on how the structure is organized. This is one of those ideas that quietly appears everywhere once you start noticing it. File systems, browsers, databases, compilers, operating systems, and AI systems all rely on trees in some form. Pretty simple once you see the pattern underneath. Thanks for watching, and I'll see you in the next video.